Of this course, wherein which we will try to cover topics in fluid mechanics. Heat and fluid topics go together. So, that is why these two courses are always back to back taught in mechanical engineering, and many of the fundamentals which is used in fluid can be used in thermal, and thermal can be used in fluid. In this lecture, it is an introductory lecture. So, we will try to see fluid and fluid mechanics, liquid versus gases, fluid as a continuum, then properties of the fluid viscosity, basic flow analysis technique, fundamental physical laws on fluid, what are dimensionless numbers, dimensionless numbers, vast scope of fluid mechanics, then manometry, working application of multiple fluids, configuration and their uses, then hydrostatic pressure, center of pressure of plane surfaces, the limits, vapor pressure and cavitation. Cavitations are nothing but bubbles. Then finally, we will try to see vacuum and the continuum assumptions. Fluid mechanics is a branch of physics that studies the mechanism of liquid, gases and plasma, and the forces acting upon them at rest and in motion, and their interactions with boundary. When the forces are at rest, it is called as fluid statics, and then in motion it is called as fluid dynamic. So, fluid mechanics is a branch of physics wherein which liquid and gases. So, if you try to take fluid, gas is also a fluid, mechanics of liquid, gases and plasma. Plasma is the fourth state of material, plasma. So, for all the three you can get. Interestingly friends, you have also cold plasma. We always think plasma means very hot, inside the sun there is plasma. You also have cold plasma, wherein which the electron densities are high, but they do not try to react and create temperature. They can be used for washing. So, liquid, gas and plasma and their forces acting upon at rest and motion against what? The interaction against their boundaries. So, continuum mechanics can be classified as solid mechanics, fluid structure interaction and fluid mechanics. Fluid structure interaction is the interaction with boundaries. When we talk about fluid mechanics, it is called as fluid statics and fluid dynamic. So, dynamic is motion, here it is at rest. Then we can try to see what happens when the fluid flows through a pipe, what are the internal and external flows which can happen, then single or multiple phase flow. Single phase is only water, multiple is you have bubbles in it. Then you can have lamellar and turbulent. In thermodynamics, we studied in the boiling, we thought that first there will be discrete films will be made and then you will be made a continuous film. So, the next one is going to be lamellar and turbulent flow. Lamellar is a smooth film getting formed on top of a flat plate is lamellar, and turbulent is when you have roughness on the surface or any undulation, there is going to be a turbulent flow which is getting created, turbulent. And then finally, groundwater flow. All these things are being statics and fluid dynamics. So, the stability problem will come here and the boundary problems come here. So, stability problem is pipe flow, a fluid flowing through a pipe, internal or external flow, inside a pipe or external a pipe, heat exchangers we found lot of applications, single and multiple phase flows. These are all stability problems. Then lamellar and turbulent and groundwater, they depend upon the boundary problem. What is a fluid? A fluid is a substance that continually flows or deforms when we subject it to a shear stress or external force. It is a continually flow or deforms when we subject it to a shear stress. What is shear stress? Shear stress or external force is fluid. A solid can resist a shear stress by a static deflection, while a fluid cannot resist a shear stress by a static deflection. So, when we have a body, when there is a shear force happening, so that is what a solid can resist the shear stress by a static deflection, while a fluid cannot resist the shear stress by a static deflection. Any applied shear stress, no matter how small, will cause the fluid to move and deform continuously as long as the stress is applied. So, you are trying to apply some stress, as long as the stress is applied, no matter how small, will cause the fluid to move and deform continuously as long as the stress is applied. A fluid at rest must be in the state of zero shear stress, known as hydrostatic stress condition. This is important. A fluid at rest in state of zero shear stress is known as hydrostatic stress conditions. So, you can see a fluid, there is a bottle, the bottle is filled with gas, right. So, when we try to do condensation, this gas, how do you condense? You can try to apply a very high pressure, this gets condensed. That is how they do the liquefied petroleum, they do the same. So, they pressurize it and then they get it condensed. So, when this tries to evaporate, when you try to heat, it gets evaporated and it forms this. So, condensation, evaporation, this is gas, and when it is compressed, it becomes a liquid. When you further try to push it, it is when we freeze it, it forms a solid. When the solid melts, it forms a liquid. This is solid. The fluid mechanics is a study of fluid either in motion or at rest. So, bottle of water is a static one. If I have the bottle through which one side it is water is pushed inside and one side it is taken outside, then the fluid is either in motion. The blood flowing through the vein, it is in motion, right. Many a times it will be difficult for us to calculate. So, what we do is we try to convert it, simplify it, and then assume it at rest and then try to solve. So, both gases and liquids are classified as fluid. The fluid encompasses an enormous number of engineering applications such as breathing, blood flow, pumps, turbines, aeroplanes and rivers. Almost everything on this planet either is a fluid or moves within or near a fluid. In fluid mechanics, we have two classifications. We call it as Newtonian fluid and non-Newtonian fluid. If the shear stress is directly proportional to the shear strain and if the line continues like this linear, it is called as Newtonian fluid. Non-Newtonian fluids are those fluids which does not follow the characteristics are called as non-Newtonian fluids. For example, ketchup is one, and you can have paste, whatever toothpaste is two, blood, all these things are non-Newtonian fluids. Within the fluids, there are two classes, liquids and gases. This distinction relates to the effect of cohesive force between their molecules. A liquid with a strong cohesive force tend to retain its volume and will form a free surface in a gravitational field if unconfined from above. Please note this point, a liquid with strong cohesive force tend to retain the volume and will form a free surface in a gravitational field if unconfined from above. The free surface liquid flows are dominated by gravitational effect. The gas with negligible cohesive force expands to fill its container and has no definite volume. The gas cannot form a free surface. There is a big difference. Free surface, liquid flow are dominated by gravitational effect. The arrangements of molecules in solid, liquid and gas. So, this is solid, liquid and gas. So, intermolecular spaces are very less. It is intermolecular space in liquid is more than the solid, and the highest is in gas. Fluid as a continuum. For typical engineering problems, the fluids are treated as continuum. This means that the fluid property like density, velocity can be considered as varying smoothly throughout the space. So, this is fluid as a continuum. So, they call it as continuum mechanics also. The continuum assumption is generally valid unless the fluid is extremely rarefied, such as gas at very low pressures or very high altitudes. The continuum assumption is generally valid. Everywhere it is valid unless the fluid is extremely rarefied. That means to say the gas is at a very low pressure or at very high altitudes. Very high altitudes, you go to a mountain and then you can see the continuum mechanics does not, or continuum assumptions don't work. So, here if this is a plot between macroscopic properties such as density with respect to surface volume. So, here you can see sample size too low, where the continuum assumption is invalid. So, here it is macroscopic uncertainty will be there. Then representative of sampling volume, which is continuum assumption is valid, is in this zone, right, where the specific sample volume is there. Then macroscopic uncertainty happens in sampling size too large we will try to have. So, we have volume and then delta, this is the thickness. To understand and analyze the fluid flow, several key properties are important. The most important property is considered as the velocity vector field, which is V, where we express in the x, y, z coordinate system, and t, z and t. So, the other primary properties are pressure, density, temperature. Pressure is a thermodynamic property, not a force. Pressure is force per unit area, is not a force and act normal to a surface. The secondary properties include viscosity. Oil has higher viscosity, ghee has much higher viscosity, honey has much higher viscosity. Viscosity, the flowing property, very important. Then thermal conductivity, specific weight, surface tension, speed of sound and vapor pressure. All these things are secondary properties which are part of fluid, and viscosity is very important. See, on a cold winter day, if you are trying to apply oil to your hair, you can see the oil is frozen. So, now what happens? You will try to generate heat by pressing it and rubbing it against two hands. The friction creates the solid oil which is frozen gets converted into liquid, and now this liquid you apply it on your hair, because the flowability of the liquid on your hair is much higher. So, viscosity is very important. Let us take a bread on which you try to apply butter. So, what happens when you have a solid bread? Solid bread and a solid cube of butter. Solid bread means a hard bread, I am saying, a cube of butter. You are trying to smear it on top of the bread. It is very difficult, very difficult. So, what you do is you try to slowly soften the butter and now smear it on top of the bread. So, there also viscosity plays a very important role. Thermal conductivity, specific weight, surface tension. Surface tension is very important. Surface tension will allow the bubble to continue to form, and then it will allow it to move in air. Speed of sound and vapor pressure. We will learn detail about fluid properties in part 2, properties of the fluid, second part of this lecture. Viscosity, a very important parameter. So, I have said viscosity is a measure of the fluid resistance to flow. If a fluid has to flow, what is the resistance the fluid gives for flowing? Water, low viscosity, which is 1.0 centipoise. Honey, which has a very high viscosity, around about 12,200 centipoise. Viscosity is a fluid property associated with its resistance to bring set of motions or resistance to flow. For common linear fluid called Newtonium, which I already told, the applied shear stress is directly, so this is tau and this is strain. So, there is a linear relationship, is directly proportional to the rate of shear strain or the velocity gradient, which can be represented of dou u by dou y. Right? It is a linear relationship. The constant of proportionality is the coefficient, is the viscosity coefficient mu. So, tau is equal to, stress is equal to strain into du by dy. The relationship is given. The key characteristics of viscous flow near the solid wall is the non-slip condition. You have a solid wall, glass. A key characteristics of a viscous flow, the oil is dropped, flow near a solid wall is the non-slip condition, where the fluid velocity at the wall is 0 relative to the wall. So, there is a wall, there is a liquid. The key characteristics of viscous flow near a solid wall is the non-slip condition, where the fluid velocity at the wall is 0 relative to the wall. What are the basic flow analysis technique? The fluid motion problem can be approached by two ways. One is called as control volume analysis, next one is differential analysis. Otherwise, it is called as integral approach. There are two approaches. One is fluid motion problem, integral approach or differential approach. Integral approach, working with a finite region, balancing flow in versus flow out to determine gross effects like force or energy exchange. This uses integral form of the conservational laws. So, working with finite region, balancing flow in versus flow out to determine the gross effect like forces or energy exchange which happens. The differential analysis, seeking point by point detail of the flow pattern by analyzing an infinitesimally small region or small element. So, there is a large one, I take a small element and I start looking at it, that is differential analysis. This result is the basic differential equation of fluid motion. So, there are two approaches. This is very important. One is integral approach, the differential approach. So, flow in versus flow out to determine gross effects like force or energy exchange. The fluid mechanics is a branch of mechanics and satisfies a set of well documented basic laws. Right? These fundamental laws applied in both integral and differential analysis include conservation of mass, conservation of linear momentum, conservation of energy, and other important relationship which include angular momentum and equation of states. The conservation of mass is nothing but continuity equation. Conservation of linear momentum is Newton's second law, resulting in Navier-Stokes equation for viscous fluid comes for the conservation of linear momentum. Conservation of energy is the first law of thermodynamics, and the other laws are angular momentum and equation of the state. What are dimensionless numbers? The fluid mechanics is a highly visual subject, and flow patterns can be visualized in many ways. For example, if you have a gas which is getting leaked out of a cylinder, one way is you can smell it. The other way is if you try to pressurize and spread a powder in the floor region, you can see how the flow patterns are done. Right? And when we are trying to do experiments, we try to have lamellar flow, a constant flow, smooth flow, and we will try to see at what point it gets converted into a rough flow. And when we want to visualize this, we use a flow pattern, can be visualized in many ways. Understanding flow pattern qualitatively and quantitatively is very, very important. Qualitatively is good, bad, fast, slow. Quantitatively is you try to tell it with respect to velocity, or you try to tell it with some other parameter. The basic line pattern used includes streamlines, streak lines and path lines. We will see that in detail. Streak lines, path lines and streamlines, basic lines. The visualization techniques can be done by particle image velocimetry that can provide the insight into the flow field, how is the flow going on. So, the dimensionless number happens because the flow patterns can be qualitatively and quantitatively understood. So, in this slide you can see dimensionless number. So, where a fluid is flowing and then between inside a glass tube, where you can see when time at t equal to 1, t equal to 2, t equal to 3, where is the line moving or where is the fluid moving. So, we saw here there are different types of line patterns: streamline, streak line and path line. So, here is an example for a path line. A fluid particle is here when t is equal to start, and it is here at t equal to n. While start to end, what is the way it travels? There it is tried to see here. The fluid particles at some intermediate times are here. So, this tries to talk about the path line. Then we would like to see the streamline. So, where the fluid is flowing on top of a boundary. So, this is the it's a smooth line which goes at a velocity. So, this is streamline. What is stream tube? Is there is a tube inside a tube. How does it form? That are the streamlines. What is a streak line? Streak line is a smoke or a dye which is trying to flow past the object. You see what is the profile of a dye which is there. So, dimensionless numbers are crucial in fluid mechanics as they reveal the basic parameter governing fluid motion. The dimensionless number parameters are is the Reynolds number, Re. The Reynolds number relates inertial effect to viscosity effect. Reynolds number, Re, relates to inertial effect, inertia to viscous force, viscous effect or viscous force. So, Re is equal to rho times VL, VL divided by nu, or it is VL by V, where VL are the characteristics of velocity and length, and the scale, the rho is the density, mu is the dynamic viscosity and V is the kinematic viscosity. Mu is the dynamic viscosity and this is kinematic viscosity. The values of this Reynolds number plays an important role to distinguish the fluid flow, whether it is a smooth flow or a turbulent flow. So, the value of Re indicates different flow regimes. One is very low regime, which is viscous creeping motion. The next one is moderate, which is called as lamellar flow, and high Reynolds number are turbulent flow. When you want to have lot of convection, we go for turbulent flow. So, the vast scope of fluid mechanics. So, the fluid mechanics touches nearly every human endeavor. It is fundamental to natural phenomena like meteorology, oceanographic, biological flow, transportation like aeroplane, ship, automobile heavily rely on fluid mechanics principle, drag and lift. Aeroplane, drag and lift, automobile, drag and lift. Energy generation, hydro, wind, steam turbine also includes about the fluid motion. Many classic engineering problems like irrigation, flood control, pipelines, pump involved in fluid mechanics, all these places fluid mechanics plays a very, very important role. So, if you look at the center viscous fluid mechanics, you can try to see here Newtonian and dynamic viscosity, Reynolds number loss under NS equation, Navier-Stokes equation, impact sputtering, then lamellar flow. Impact sputtering will happen on coating, right. then lamellar flow happens in and lamellar flow and turbine in turbulent flow in the ships, boundary layer problem in the layer theorem in the heat exchangers and previousness. Then you will have simulation and algorithms in automotive engineering and aeroplane engineering. Manometry and its principle. The manometer is a device specifically used to measure the pressure difference between 2 points. Pressure difference between 2 points. It is a type of gravity based pressure measurement instrument. It is based on the principle of hydrostatic force, constant pressure. The change in the elevation of the liquid is equal to the change in the pressure. Specifically, the pressure change P2 minus P1 is equal to gamma times Z1 minus Z2, where gamma is the specific weight and Z2 minus Z1 is the elevation change. So, the pressure change can be equated to gamma times Z1 minus Z2. Z1 minus Z2 is the elevation change, specific weight. Thus, a static column of one or more liquid or gases can be used to measure the pressure differences. So, you can try to have both end open, one end open, one end close, and then you can have both this thing. For example, you wanted to pump from a tank of kerosene to a small container, you can use this mechanism. When we are trying to do elevation, this is what you do in your class 8 or 9 experiments, wherein which you try to figure out the change in pressure with change in height. So, the working of a manometry, the pressure difference is balanced by the height difference of the fluid column. So, you have a fluid column ZA, then this is ZB. So, you have a PA, PB, and there is a difference called H. This is the density of the liquid, whatever it is. For multiple fluids, the pressure change through each fluid is calculated separately as they move from one liquid to another. So, this is U-type manometer. This is enlarged end manometer, enlarged end. This is enlarged end manometer. This is inverted U manometer. This is U manometer, inverted U nanometer, and this is inclined limb manometer. For a single fluid column of height h, the difference is delta z, the specific weight is gamma. So, the change in pressure rho, the delta p is equal to specific weight into height of the fluid, which is h. So, P2 minus P1 times divided by gamma is equal to Z1 minus Z2. So, if h is nothing but Z1 minus Z2, so P2 minus P1 will be delta P, which is gamma times h. This is the formula relationship. Considering moving from point number 1 to point number 5 through multiple fluids. For example, this is first you have oil, then you have water, then you have glycerin, then you have mercury, and then you have mercury, and finally you have something else. So, now the pressure will be P2 minus P1. P2 minus P1 is equal to rho Pg. This is rho Pg into Z2 minus Z1. Next will be 3 to 2, P3 to P2 will be equal to rho times G, bracket you will try to have Z3 minus Z2. Then here it will be Z4 minus Z3, Z5 minus Z1. So, the summation will be P5 to P1. So, considering moving of from a point 1 to point 5 through multiple fluid columns is illustrated in this figure. So, where is the application for multiple fluids? Start at a point P, add or subtract pressure change from the first fluid column is specific weight into delta Z1, add or subtract a change in the second fluid is this, add, so equal to 5 you will have all these things done. So, the sign depends on whether you are moving down through a fluid column or not, moving down or moving up. That is the sign, that is why I said plus minus. So, the configuration and the use of a manometer. So, here if you see a U type manometer, there is a scale which is there. So, from here there will be atmospheric pressure. then the pressure to be measured will be moving here. So, the difference will be delta H or H. So, the classic configuration is the U-tube manometer. The manometer are used to measure the pressure drops, not the pressure drop, such as the cross section in a pipe or flow measurement device like orifice plates. Orifice plates are, you have a small hole and then you in a plate. They can be used with instruments like pitot-static tube to measure the flow velocity by measuring the pressure difference. So, this is important. So, here in the first one you found out the pressure drop. So, they can be used with this manometer, they can be used with another instrument like pitot-static tube to measure the flow velocity. So, what is the definition and the principle for this manometer? So, we saw manometer is used to measure the delta P, right. So, the manometer is a device used to measure pressure difference between 2 points. It can work on gravity based measurement. It is classified under gravity based measurement device. It works by utilizing a static column of one or more fluid or gases. The fundamental principle is based on hydrostatic formula. The change of elevation of a liquid is equal to change in the pressure. So, what are the key hydrostatic formulae of manometer? This we already saw. So, this for a single fluid column with a height difference h and a specific weight gamma, the pressure difference is in gamma times h. The relationship between P2 minus P1 gamma times means the pressure change difference is equal to specific weight into elevated difference. When the same manometer is using multiple fluids, then what do we do? When move from one point to the another through a series of connected fluid columns. So, that is what in a series of connected fluid columns, the start at the pressure of the initial point P1, move through each fluid column adding the pressure change gamma times Z. If moving downward or subtracting it moving upward, use the specific weight gamma for the fluid column. So, this can be represented in this way. So, the plus minus comes from the pressure change, positive and negative. The sign depends on the direction of movement up or down through the column. So, what is hydrostatic force? Hydrostatic force on submerged surfaces. When we are trying to take a cup and when we are trying to move the cup, keep it at the atmosphere, try to take the same cup, go 10 meters below the sea level, go 100 meters below the sea level, you can see the cup deforms. So, that is what we said on submerged surfaces. Motivation of this motive of study is many fluid problems associated with static fluid and their effect on solid surface such as submerged bodies. The design of containment structure like tank, dams require computing of hydrostatic forces. So, where does this hydrostatic force come from? The fluid at rest cannot support shear stress. This means that the stress on any plane within the fluid, static fluid, is purely normal and is called as fluid pressure. The pressure is a thermodynamic property of a fluid. It is not a force itself, but it creates a force on a surface due to fluid molecules. This force is always normal to the surface. Hydrostatic, it is always normal to the surface. This is a surface, normal to the surface. The static fluid under gravity, pressure varies with depth. This pressure distribution results in a net zero on any submerged surface. The hydrostatic force come into existence. So, the hydrostatic pressure distribution follows the same principle. Delta P is equal to specific weight into the height difference. The formula shows the pressure increases linearly with respect to depth. So, as and when you go down, the pressure linearly goes, that is what they say. The plate element, the element connected to the node, and when you go to heights less than H1, H2, H3, H4, H5, then you can see the pressure which is plotted P1, P2, P3, P4, P5, P6, and here is a gradient, this is a fluid flow. On submerged surface, the concept is for a plane surface submerged in liquid, a plane surface submerged in liquid, the pressure varies linearly with depth. The hydrostatic force is a resultant of the distributed pressure force over the surface area. When you want to calculate the total force, the hydrostatic force F on one side of the submerged plate panel is given by integration of pressure over a delta A. So, this is the formula. The total hydrostatic force F on one side of the submerged plane is given by integral of pressure over the surface area, which is P A plus specific weight into H into dA, where P A is the atmospheric pressure at the free surface and A is the depth area element. So, the center of pressure for a plane surface C P, this is calculate the total force. So, here we are trying to do a center of pressure C P. The hydrostatic force is a distributed load, but for engineering calculations it can be represented by a single resultant force F acting at a specific point on the surface. So, the point is called as center of pressure. The hydrostatic force is a distributed load. So, when you take, as I told you, deep into the water, the pressure is distributed all around the object. But for engineering calculation, it is represented as a single point, single resultant force F acting at a single point. The point is Cp. The location of Cp is very important because the pressure increases with depth. The pressure is higher on the lower part of the submerged surface. Therefore, Cp is always below the centroid of submerged plane surface in a uniform gravity field. This is important. So, the fundamentals of fluid pressure. The fluid pressure is a force exerted by a fluid on a unit area. The pressure can be measured relative to different reference plane. Absolute pressure measures relative to a perfect vacuum, absolute zero. Absolute pressure measured relative to a perfect vacuum. Gauge pressure is measured relative to the local atmospheric pressure. So, gauge pressure is absolute pressure minus the atmospheric pressure. So, gauge pressure measured relative to the local atmospheric pressure. The vacuum pressure is the term is often used for pressures below. Vacuum is below the atmospheric pressure. It can be rated as negative gauge pressure. The vacuum pressure is a positive value when the atmospheric pressure minus the absolute value. So, you have to understand the terminologies. What is absolute pressure measured relative to the perfect vacuum? What is gauge pressure measured relative to the local atmospheric pressure? So, absolute pressure minus atmospheric pressure gives you the gauge pressure. Then vacuum pressure below the atmospheric pressure it gives. It is always negative pressure gauge. Then vacuum pressure when positive, when atmospheric minus absolute you get the positive. A vacuum is theoretical state where pressure is absolutely zero. This is very important. Absolutely zero. This means there is no fluid molecule present to exert force. When it is vacuum, a vacuum is a theoretical state where pressure is absolutely zero in the vacuum. In reality, achieving a perfect vacuum is practically not possible. Even deep inside the sea, there are some particles. So, it is not possible. That is why they said theoretical state. The fluid mechanics, when we talk about vacuum, we visualize a region where the absolute pressure is significantly lower than the atmospheric pressure. What is absolute pressure? Measured relative to a perfect vacuum. Right? For example, atmospheric pressure is often 101 kilopascal. A pressure of a 50 kilopascal absolute would be a vacuum condition relative to the atmosphere equivalent to the gauge pressure of minus 51 kPa or a vacuum pressure of 51 kPa. So, now we are able to understand 101 minus 50 is 51. So, here we are saying gauge pressure means it is equivalent to minus kPa and vacuum pressure. So, vacuum pressure this term is often used for pressure below the atmospheric pressure. It can be thought of as a negative gauge pressure. That is what is minus 51 K. So, there are lot of occurrence of low pressure in flow. The low pressure regions where approaching vacuum condition relative to the surrounding occurs in various fluid flow. Vacuum cleaner, the device works to create a low pressure region to draw the air. It sucks. And then when you try to drink cool drinks through your pipe, through your straw, the device works by creating a the lower pressure region to draw air and particle in. Then pumps and turbine is a low pressure can occur on the suction side of the pump or the specific area within the flow machinery. The biological system, the human lungs can create negative pressure to draw air or liquid estimated around about 3000 Pascal below the atmospheric pressure for drinking a milkshake. So, look at it, the vacuum pressure it creates. So, the limitation, vapor pressure and cavitation, every liquid has a vapor pressure that depends on the temperature. We have seen it in the thermodynamics lesson. Every liquid has a vapor pressure that depends on its temperature. This pressure at which the liquid starts to boil or vaporize is vaporization. This is the vapor pressure. If the absolute pressure in a liquid flow drops to a liquid vacuum pressure, the liquid can flash into vapor forming bubbles. If the absolute pressure in a liquid flow drops, absolute pressure in a liquid which flow drops to liquid vapor pressure, right, then the liquid can flash into vapor forming bubbles. Cavitation is the phenomena where the vapor bubble forms in low pressure region and then collapses violently when they move into high pressure region. Cavitation is the phenomena where these vapor bubbles form in low pressure. So, the bubbles which are formed are in low pressure, and when they collapse they create very high pressure. It is like a balloon, right? When the balloon collapses, it will be a high pressure. So, when this vapor pressure forms a low pressure region, this is a low pressure region. When the cavitation can cause noise, vibration and severe damage to machinery. That is why we try to avoid two-phase flow, liquid and steam, right. We try to have dry steam. So, it is because of this cavitation effect which is there. So, the vacuum and continuation assumptions. So, you can see there is a pump and then there is a chamber. So, the continuum viscous flow is there. So, the water flows from here and the pump is pressurizing to go up. So, the chamber pressure is lesser than the pump pressure. In many engineering problems, we treat fluid as continuum, assuming the properties like density and velocity vary smoothly. The continuum assumption is valid when the scale of the flow is much larger than the average distance molecule travel between collisions, that is the mean free path. When the scale of the flow is much larger than the average distance molecule travel between collisions. At very low pressures approaching hard vacuum, gases become rarefied, the distance between the molecules increases and the mean free path becomes comparable to the flow dimensions. That is why the continuum equations when you do in micro scale is a challenge. So, friends, what did we study in this full chapter is we studied what is a fluid, then what do you understand from fluid mechanics, what are the key properties like fluid viscosity, then loss of fluid, then dimensionless numbers, then fluid pressure measurement where we talked about manometer, then hydrostatic forces, and finally we discussed about pressure concepts and cavitation. Cavitation is created because of low vacuum. The cavitation is a phenomena where these vapor bubbles form at very low pressure, and when it bursts it creates a high pressure to collapse. So, these are the references, friends, we used for making this chapter, and I am sure you would have enjoyed this lecture. We have tried to cover the basic fundamentals of fluid mechanics and some properties of fluids. Thank you.